Welcome to the fourth and last module of this short course on machine learning in communications. In lecture 7, we are going to continue our discussion on unsupervised learning, which we started in lecture 5. In this specific lecture, we are first going to continue our discussion on Gaussian mixture models and learn how to capture clustering in the data by using Gaussian mixture models, which is something we started in lecture 5 already. Once we model the data using a Gaussian mixture model, we'll show that the problem reduces to determining the parameters of the model. So you can show that your density estimation problem is equivalent to just learning the parameters of your Gaussian mixture model after you've chosen that as a model for your data. And these parameters will be determined using this idea of expectation maximization, which is something that you really need to know. This is a very useful algorithm, appears very frequently. And along the way, we will also make an interesting connection of k-means algorithm with a very specific Gaussian mixture model. So by specific Gaussian mixture model, I mean so we are going to make a couple of very specific assumptions about the Gaussian mixture model, and then we'll see that this density estimation problem is related to something that we were doing in k-means as well. Right, so so the reference for this material will be Kevin Murphy's book, which we also referred to, right, in our lecture 5. And here, I would also like to thank my former colleague, Professor Dhruv Batra, who was at Virginia Tech before. His course on machine learning taught me a lot of what I really know about this topic, especially from the core machine learning and data science perspective. And naturally, some of the notation that I use is also sort of inspired from the way he set up the problems as well. Okay, so let's introduce what we are trying to do, right? The density estimation problem. Let's define what the problem is. So we are given a data set X, right? Same notation as before. This is our data set, which is nothing but a collection of d-dimensional vectors. There are n of them. So these are our examples. You can think of these as examples or data points and so on, right? There are n of them. Now the goal is to come up with a distribution P that describes this data set. In other words, we fit a distribution P, right, to this data set. Now, in this lecture, we are going to model this distribution P as a mixture of Gaussians. Okay. Now, most of our discussion in this lecture will actually is a little bit more general and hence applicable to general mixture models as well. But in order to keep our arguments concrete, I will just limit it to the mixture of Gaussians. Now, since we have introduced Gaussian mixture models already in lecture 5, let's just recall our notation from that lecture. So in Gaussian mixture models, we have latent variables, right, which we denoted as Zi, right? Zi will take one of the k values, right, 1, 2, so on up to k. We are assuming that in our Gaussian mixture model, we have a total of k Gaussians. Right, and probability Zi equals to j is pi j, just a categorical distribution. Probability that your point I comes from the jth Gaussian is just pi j. And this general discrete distribution is also called categorical distribution. Categorical distribution, right? We already discussed the role of latent variable before, so I'm not going to go into this in detail again. So the second part of our notation is the likelihood, right? Once you know from which base distribution, right, your point is coming, then you need to write that base distribution, right, conditioned on your latent variable. So that is what the likelihood here is. So since we are working with a Gaussian mixture model, so what we are going to assume is the probability right? X, or in this case, it is the probability density function of your data example, xi, conditioned on the fact that this was produced by the jth Gaussian, right, is nothing but this multivariate Gaussian distribution, right? So I'm sure a lot of you would have already come across multivariate Gaussian distribution. So I'm not going to go into this expression in a lot of detail. It's very standard. If you haven't come across this, just check this out. It will immediately make sense. So let me just describe the key variables which will come in our estimation problem. So here, mu j, which appears here and here, this is just the mean vector, right? If I write, for example, my data example as say xi1, xi2, xid, right? Mean vector is nothing but the mean of each of these variables, right? So likewise, there is this second variable here, which is sigma j. This is nothing but the covariance matrix. So this generalizes the idea of variance to a vector. So this is the covariance matrix. So just as more well-known 1D Gaussian expression, right? Just like that expression. So your variance appears both here and also in this constant multiple where there is a sigma squared term in the denominator. In multivariate Gaussians, we get a determinant of a covariance matrix. Okay, so just check this expression out. There is nothing too complicated about it. Now let's write the objective, right? Once we have the latent variable, which again gives us the probability that a point is generated by a specific Gaussian, where you can think of 1, 2, so on up to k as the labels of the Gaussians, and you have the likelihood, which is nothing but multivariate Gaussian distribution. You can write the objective as the estimation of all the parameters that appear in these two distributions, the categorical and Gaussian, for every point, okay? So you can write the parameter vector as theta, right? So this will appear in pretty much all the slides. This is just containing all the parameters that we are estimating, right? So my first set of parameters are pi, which are nothing but pi1, pi2, so on up to pi k, right? The categorical distribution. So this is my shorthand notation for that. And my second set of parameters are just the mean vectors for the k Gaussians that I'm choosing. And this is the set of covariance matrices for the k Gaussians, right? Now, for this set of parameters, let's look at the maximum likelihood estimation problem, which will also reveal a specific form, which will inspire a lot of what we are going to do in this lecture. Okay. So the maximum likelihood problem of the setting that we already described in the previous slide is nothing but, so you write along the same lines of module 2, where we had a lot of discussion about these type of problems. What you do is you assume that all the examples are IID, right? Examples given to you in the data set are IID from the underlying distribution, which in this case is P, which is what we are trying to estimate, right? Then using that IID property, you can write this as your likelihood as product of the probabilities corresponding to each term. Then you can write your log likelihood as summation of the log of the probabilities, which is appearing here, right? This is nothing but log likelihood. And you maximize over this log likelihood, and whatever theta maximizes over this log likelihood, right, becomes your maximum likelihood estimate. So this is something we have already done, and I hope most of you are very familiar with this notion by now. Now, what is new here is the presence of latent variables. Note that we have a distribution corresponding to the latent variables, which we also need to estimate in this problem, which means that latent variables have to appear explicitly in our problem setting, right? So the way you do that is you introduce zi equal to j, right, my latent variable, and then you marginalize over that, right? So you write basically the joint distribution, right, and you marginalize over zi, you basically get your original expression back. So you basically get this form here. It should be very easy for you guys to understand. We are just marginalizing over Zi. But now the problem that we get with this marginalization is the fact that we have a summation within the log, right? So I'm going to call this a log sum form in this expression. Until now, if you think about all the likelihood functions that we have seen, we never really had a summation inside the log. We always had a summation over the log, right? Now this actually is very problematic if you think about it, and you can check Kevin Murphy's book, chapter 11, for a lot of discussion related to this. But the crux is that if you now try to maximize over a given variable, because you have this summation inside the log, you're not really going to get a nice separation of different terms, right? You are going to have a very strong coupling across different parameters, because of which maximization is going to be an issue. And in order to understand that a little bit more, maybe carefully, let's contrast this with what we already know, right? So the unknown here is Zi. Right? So as I claimed before, the problem comes because we have this hidden variable. Now, what if somebody actually tells you what Zi is, right? Let's say Zi is not latent anymore, which means we had a labeled data set. Let's say we had a labeled data set where we had this feature xi and corresponding label Zi, which, by the way, is what we are trying to learn, right? This is hidden to us in the original problem. But what if, just for the sake of argument, we assume that Zi was given to us? Now, if you try to write the ML estimate in this case, ML estimation problem in this case, you actually get a very nice form, very familiar form, I should say, which we have seen plenty of times, which is the form here, right? So you notice that, so this basically comes by, so if you try to write the joint, right, P of xi, Zi conditioned on theta, that can be split into two terms, P of xi given Zi and P of Zi. That's why you're getting these two terms here. And we see that, first of all, there is no summation within the log, and there is nice separation of parameters. And by that, what I mean is this term here will contain only the parameters corresponding to xi, right? This term will contain parameters only corresponding to Zi. And if you remember the type of calculations we did in module 2, this separation was really the key for a lot of our calculations to go through, right? Here, on the other hand, you get this summation, which is coupling a lot of different parameters, and that becomes problematic. Okay? Now, what this tells us, right, what this very sort of little discussion tells us is, if there is a way to complete our data, if there is a way to say something about the hidden variables, that's going to make our problem easier, right? And that is the central argument we are going to use to develop a lot of what we are going to do in this lecture. Okay, so let's first look at one easy way of handling this log sum, right? Or I should say maybe getting rid of this summation within the log. And that is through hard assignments. This is something we have already done in the context of k-means in module 3, right? So what we are going to assume here is that probability of xi comma zi equals to j, right? If I write this probability, this is nothing but, this should be xi here. This is going to be 0 for all choices of j except one, right? It is going to be non-zero only for j equals to ci, and I am choosing ci here to actually connect this to k-means. If you remember our discussion on k-means, ci was what? Ci was our assignment of points to the clusters, right? Now just keep in mind, think of clusters as Gaussians for now, and this whole discussion you can very nicely connect to k-means, and then I will wrap everything up in the next slide. So this is my assignment. Think of this as hard assignment. Each point is assigned to only one Gaussian, right? There is no probabilistic or soft assignment, which I implied in my original setting. And we'll of course go back to the soft assignments very soon. Okay, now in order to make a connection of this Gaussian mixture model with k-means, let's make two more assumptions, okay? Again, these assumptions are, again, just for making a connection with k-means. I'm not saying that these assumptions will stay with us throughout the whole lecture, right? These are just for a couple of slides. So first, I put uniform distribution on Zi. I assume that P of Zi equals to J is simply 1 over K, right? And then I assume the so-called spherical Gaussians, which means that my covariance matrix is nothing but a scale identity matrix, right? This is nothing but sigma squared identity matrix. Okay, so now if you try to write your the density, right, of xi, assuming that the point is coming from the jth Gaussian, right, just your likelihood, that will have this more familiar Gaussian form, right? If you now have d equals to 1, this reduces to maybe a form of Gaussian that you might have come across maybe more frequently, right? So nothing complicated here. Just if you make these substitutions in the expression of PDF that you already introduced for multivariate Gaussian, it will simply reduce to this, right? I'm not going to go through all that because we have a lot to cover in this lecture already. So now if you try to write the maximum likelihood for this case, right? Let's just look at each of these expressions carefully because it is going to reveal something quite interesting, as we'll see. So this, by the way, is just by definition, right? My ML estimation. I am just maximizing over the log likelihood, as I said before. Now we have these latent variables Zi, because of which we get the log sum form. We have already seen these two steps on the previous slides, right? Now, what new I'm going to do here is the following. I'm going to, as we discussed in the previous slide, I'm going to assume hard assignments, which means, let me erase this part, which means that only one of these k terms is going to be non-zero, right? That is my assumption. I'm just forcing all the other probability terms to be 0, and I'm just retaining 1, and that basically means hard assignment, okay? So I know that from the notation I've already introduced, the term that corresponds to the hard assignment is Zi equals to Ci. So Ci is my hard assignment here, okay? So I get rid of this summation within the log, right, by forcing all the other terms to be 0. And now I can write this P of Xi Zi, right, the joint, right? I can write this as product of marginal and conditional, right? And if you just substitute the distributions which we know already for these, so this is nothing but a uniform distribution. We have already made an assumption for that. And this is Gaussian under that identity covariance matrix assumption. And if you substitute all these expressions, what you get is something very beautiful. You actually get this expression. So this is ARG max over negative of something that we have already seen, right? Or let me actually write this in terms of argument so that the idea becomes even more clear. 1 over n summation I equals to 1 to n xi minus mu ci squared, right? And let me write the remaining term in a different color, 2 times sigma squared. So the terms in red color here, right? So they should be familiar to you. We introduced these terms in the context of k-means, right? Where we interpreted this as the average distortion. We said that k-means, right, is just an approximate algorithm to minimize the average distortion. And we never really had this sigma squared additional term because we were not doing density estimation. We were just doing clustering, right? So this reveals something quite interesting about k-means. So what k-means does is it really is in a way doing this clustering of data, assuming if you connect it to a Gaussian mixture model, assuming that you have spherical Gaussians, right? So now you can, just like our discussion on supervised learning before, you gain intuition as to in what type of data sets is k-means going to work quite well, and likewise in what data sets is k-means likely going to not work very well. So let me draw one cluster of points. Let's say you have a cluster of points which looks something like this. Right? Let's say it's a two-dimensional space. It's more like an elongated cluster. You don't really get a circular, nice, sort of a circular cluster of points. It's sort of a bit more elongated. Now, unless you do some specialized, unless you use some specialized distance metric, right, to account for these type of data sets, you simply use, say, Euclidean distance, then k-means may not work very well here, because as we have seen here, k-means implicitly assumes spherical Gaussians, okay? So I just wanted to make this interesting connections along the lines of what we discussed with supervised learning, right? That there is this base sort of Gaussian mixture model that can provide very similar insights like we discussed for linear or logistic regression before. All right, so now we are ready to introduce this very useful idea of expectation maximization for density estimation. We don't really need any assumptions here along the lines of what we just did. In fact, whatever we are going to discuss now is also applicable to more general mixture models which go beyond Gaussian mixture models. Okay? So let me first introduce the general idea and explain the name and sort of introduce some terms which we are going to come across, right? More like giving you a preview of what we are trying to do, okay? So expectation maximization contains two steps. There is an expectation step and a maximization step. We just iterate between these two steps, okay? We'll understand what these two steps are doing. But at a high level, what an expectation step does is it finds soft assignments of points to Gaussians. Okay, so in the expectation step, we are basically estimating these probabilities. What is the probability that your point I came from Gaussian J, right? And what it does is, once you have these assignments, you can think of these assignments as soft labels for your data. So you can say that once you have these assignments, you actually have, in some sense, complete data. And as we saw before, once you have complete data in the sense that your latent variable is no longer hidden, right? We know that things start becoming a lot more tractable, right? Now, the reason this is called the expectation maximization is once you have these soft assignment of points, you can write something called the expected complete data log likelihood, right? Expected complete data log likelihood. I will explain what this is, why this is expected of log. We'll see all that in a minute. But the expectation step at a high level is giving you the assignments, right? Now the maximization step is under the assignments, right? It will maximize the expected log likelihood to update the parameters theta. Okay, that's all what is going on here. Now, at this point, it is very natural to wonder, right? Sure, we understand by now what a log we understand likelihood, we understand log likelihood. Then what exactly is the expectation of log, right? What is expected complete data log likelihood? We will understand that very soon. The really sort of the central role that is played by this expectation. Okay. So now we are going to go through some steps, right? Just to understand how to implement expectation maximization. And then I am going to provide some intuition as to what it is doing in a few minutes, right? Now in step 0, right, which is really your initialization step. You have your set of parameters theta. So you initialize your theta as theta 0, okay? And remember, your set of parameters in the general case is your categorical distribution, then your mean vector, and then your covariance matrix, right? For all Gaussians. And one way to initialize some of these parameters is just running k-means, right? And coming up with one very sort of crude estimation of where your Gaussians should be placed, right? Just one of potentially many ways. Okay, so let's write the expectation step. I don't want to just show a lot of equations and nobody really gets anything out of it, right? So let's just write a few steps just to see what we are really trying to do in the expectation step. So at time t, right? So when we run this expectation step, say in the tth iteration, I'm going to call that at time t, step at time t, we have a set of parameters as theta t, right? So these theta t have already been estimated in the previous, say, time step, right? From the maximization step. So we have those parameters already. So we are going to do this calculations for this model or for these values of theta. Now, given theta, we can find the assignment probability of ith point to the jth Gaussian, which we are going to represent as Aij at time t is probability Zi equals to j for this data point under this model, right? Now, this is just a conditional probability. I can write this. I'm just going to apply Bayes' rule, essentially. I'm going to write this as P of xi Zi equals to j divided by pxi, right? Now I can write this equivalently, right? Just basically just applying Bayes' rule, P of Zi equals to j for the model, right? For the parameters that are already known, xi Zi equals to j again for the parameters that are known, and the denominator is just a normalization term, which can also be written in the same form, probability of xi Zi equals to j theta t, right? So let's see, is this something that we can compute now if we have all the model parameters? The answer is yes. If you look at this term here, this is nothing but pi j that comes from my categorical distribution. This is nothing but Gaussian with mean vector mu j and covariance matrix sigma j, right? So if I know my theta, which is the assumption I'm making, right, this vector theta, I know these distributions, which means I can estimate Aij at time step t. Okay, so this is really the expectation step, which is to compute these soft labels or assignments, and we'll see how to use them in the maximization step in a minute. Okay. So as I have written in this slide, so this slide, in case you're watching this later, you can just freeze this, and this really contains all the calculations we just did, right? So this gives us soft assignments of the points to Gaussians, and as I said before, sort of completes our data in some way, okay? All right, so now let's see how to use, right? In what context are we going to use these soft assignments? They are going to be used in the maximization step, right? So the way we use these soft assignments is to write this expected log likelihood, which is given here, which is given on in this expression. So why is this called the expected log, right? Where is the expectation over the log? Remember that this is nothing but probability mass function. So you can think of this summation here as expectation, because this is summation over PMF times this term. So this is basically just expectation of this log with respect to our assignment probabilities, which for a given I is nothing but a PMF. Okay, PMF for given I. So this is the reason why this is called the um, expected log likelihood. Now, this is actually in a form that we really know very well to handle from our previous lectures, especially from module 2, right? Because we don't have a summation within the log. The summation is outside, if you can see here, j equals to 1 to k. We do get sort of a weighted, right? We get these weights AI, JT, but they are not very difficult to handle. The more important part is that the summation is outside. If you now try to do a maximum likelihood estimation of different parameters for this form, that's not very difficult to do, right? Let me just write a few expressions here. Now, if you find the estimate for your categorical distribution, this will be nothing but pi j. I'm going to write this as hat t plus 1. This will just be I equals to 1 to n aij t, right? Remember, in this step, we are assuming that the soft assignments are given to us. We are assuming that aijt is given to us, right? So this is how we are iterating. From the m step, we get theta, and we use that in the e step to obtain the assignments. From the assignments, we get the from the E step, we get the assignments and we use those to obtain theta, right? So this is now nothing but I equals to 1 to n, j equals to 1 to k, ai, j, t. Right? This denominator is nothing but n. You can very easily argue that. So this just reduces to 1 over n, I equals to 1 to n, ai, j, t. Right? So you can think of this as, what fraction of mass is associated with each Gaussian, right? That's really what this categorical distribution gives us. Now, if you want to write the mean vector, the estimated mean vector for the jth Gaussian at step t plus 1, this is nothing but the weighted sample mean. Right, so previously we just got the sample mean. Now the difference is that we just have these weights, aij, they just come in your averaging. That's really the only difference between this and the case we studied before, right? The fact that you have this summation outside the log, right? If you try to just take the derivatives, you still get that nice separation of different variables, because of which writing these estimates in closed forms is possible. Okay. Again, as before, everything that I wrote, in addition to also the covariance matrix here, right, which is something I didn't write. So everything is on the slide in case you want to check this out later. Similar to your mean vector, you can also write the estimated covariance matrix, and that is also just the weighted average. So here, the difference is, as we do in the estimation of covariance matrices, you use your estimated mean vector to find this matrix, right? So here, this matrix is nothing but the outer product of two vectors, right? And then you just average over this, which is, in this case, weighted average. If this weren't, right, this specific form where we have these weights, then it would just have been, again, sort of like a sample mean, okay? So estimating, so the problem really reduced to pretty much a standard maximum likelihood estimation with Gaussians, once you have these soft labels of the data. Okay, so with this, you really have everything you need to actually implement expectation maximization if you wish to, right? We know how to implement the expectation step, which is to find the soft labels. We know how to implement the maximization step, which basically is to update the parameters, right? What I haven't told you though is why this expected log made sense, right? Why did I magically just put the summation outside? I never really told you that. So let's, in the rest of this lecture, let's just try to understand that point clearly. Okay. So what I claim is that this expected log likelihood that we got is a lower bound, but it is actually a special lower bound in the sense that it is going to touch our original function in a special way. We'll see what I mean by that. It's a lower bound but we are going to show that this lower bound is not going to introduce any penalties for us. Okay. So in order to do that, let's first recall what our key expressions were. We have this M step, right, in which we got the expected log likelihood. The expected log likelihood is just this summation here. I just wanted to again clarify that Aij, this should be Aij at time t, it's nothing but just the PMF that your point xi is coming from the jth Gaussian under your model theta t, for example, right? So this should also be theta t here. Now, if you revisit the original objective function, right? Your original objective function is the one that contained this log sum. So what I'm going to do now is I'm actually going to start with this expression, and I'm going to somehow recover this expression from the original objective. Okay, so that is our objective of this calculation here. All right. And for that, we are going to apply Jensen's inequality in a specific way, right? So let's see. Here, I'm going to introduce a generic distribution Qi, whose PMF is given by this Qij, right? So it's just a vector, right? Which is essentially just a generic PMF that I have chosen. And using this, I'm going to manipulate my original objective function. So let me write my original objective function first. So my original objective function is theta star, which is arg max over theta I equals to 1 to n log j equals to 1 to k probability xi zi equals to j given theta. Right, and also, by the way, as we discussed in, I believe it was module 2, when I just use p, right, I sometimes just call it probability. It could be probability density, it could be probability mass, right? It really depends on the nature of the random variable we are dealing with. We are just using a common notation throughout, right? We clarified that in module 2. So when I speak, I may not be very precise, right? When I just say probability, I just mean a probability term. It could be mass, it could be density, okay? All right, so what I'm going to do now is we have this summation over j inside the log. So I am going to multiply and divide by this Qij term from a generic distribution that we obtained, right? Or we just chose. We again, you could choose any distribution. We'll see that we actually want a specific form of this distribution, which will appear from this derivation, okay? But at this point, it's just any generic distribution which will work. So I'm going to multiply and divide by Qij. So this is the division term here, and this is the multiplication term. Qij is a PMF, right? So now you guys tell me, can I treat this part here as an expectation over the first term, where the expectation is taken with respect to the PMF Qi, right? It's just summation of something, right, multiplied by the PMF. So it's basically just the expectation. So I can then write this log term. Let me just write this complete log term. I can write this as log expectation over this new distribution, right, that I just chose. P of xi zi equals to j for this model, right, divided by Qi j. Now, log is a concave function, so I can apply Jensen's inequality. I have log expectation, right? This will be lower bounded by the expectation of the log, so I can write this as bigger than equal to expectation over this generic distribution, right? Log P of xi zi equals to j, right, divided by Qij, right? And also note that these distributions we have chosen, right? We have actually chosen one distribution for each point. We'll see why that is meaningful. Okay. All right. So this is what I just wrote, right? Everything on the slide again for your reference, written in terms of maybe easier to see symbols, right? And we will look at this lower bound more carefully in the next slide. This lower bound, I mean. Now our idea here, we introduced this Qij, right? And we have gotten rid of this summation, which was inside log, by treating that as expectation and then taking expectation outside the log using Jensen's inequality, right? That's really what we have done. Now my goal is to select a specific distribution Qi that will provide me the tightest lower bound, right? What will be Qi that provides me the tightest lower bound? That is what I am trying to do here. Okay. So here there are a few expressions. So let me go over them carefully. Let me go over them carefully with you. So the lower bound we obtained on the original likelihood, right? Remember, it was summation over I equals to 1 to n, right? Then there was expectation over a log term, right? So what I have done here is I have just written that expectation again as a summation, right, over that term multiplied by the PMF. So this, recall, is nothing but an expectation. Okay. So what I'm going to do now is I'm going to write this term, the joint term, as probability Zi equals to J conditioned on Xi theta times probability Xi for this model theta. I do get a product within log. So then what I'm going to do is I'm going to write this log of A times B as log of A plus log of B. So that's why you see two terms in this step. So let's look at this step carefully now. Okay. So I'm going to first look at the second term that we get in the log. So that second term will correspond to this probability here. All right. So this is the second term that we get. And here, notice that this summation is over I, this summation is over J. Now this term only depends on J, which means that I can take this summation and I can actually put this at the end because there is really no dependence of the other term on J, right? And this summation, as you will notice here, right, for every I, we have chosen this PMF. For every point I, we have chosen this PMF. So this is summation over the PMF, hence it's a 1, right? So this term is actually equal to 1. I mean, this term here. Maybe I should just write this is equal to 1, which means what I get, right, after I use this idea, right, that this is just summation over PMF, after I use that fact, you basically can reduce this second term to I equals to 1 to n P of Xi for this model. And if you think about it, this is actually our original objective function. This is our likelihood. Oh, this should be, so this should be summation I equals to 1 to n. This should be a log. This is just log likelihood. Log of P Xi conditioned on theta. So this should also be, I think I made a typo here. This should be a log. Right, so this is nothing but our original log likelihood function, right? Now remember, this was a lower bound to our original function, right? And we have shown that our second term is actually the original function, which means for this to be a lower bound, my first term should be negative, right? And it can actually be shown that this first term is the negative of KL divergence. KL divergence by definition is non-negative. So negative of KL divergence is actually negative, right? So everything checks out. This is indeed a lower bound where you can treat this term here as a KL minus of KL divergence between the following two distributions. Distribution that you chose, QI, and the soft labeling, P of ZI, XI, theta. Right? So this is my first distribution, QI, arbitrary distribution that I chose. And this is the distribution that I have been using in the expectation maximization. Right? So my first term, the term corresponding to this negative of KL divergence, will actually be 0 if I select my distribution QI to be equal to, if I say that QIJ is nothing but P of ZI equals to J, my soft labels, right? And this was nothing but AIJ, just the soft labels. If I make this choice for QI, then my first term goes to 0 and my lower bound actually reduces to the original objective. Right? So I've gotten rid of the summation that I had in the log, right? I have brought that out by using a lower bound argument using Jensen's inequality. And then I've shown that there is a specific choice of QI with which I can show that my lower bound actually is the same as the original function. Okay. Now, one tiny step that is left here is to actually show, right, that the lower bound we obtained on the previous slide is in fact the same as the expected log likelihood that I was using before. So let's just, very quickly look at that. It's quite straightforward. Now, our lower bound from the previous slide, right? If you are following all the notation, right? It's a little bit notation heavy, so I apologize for that. If you have been following everything, right? This is really the lower bound that we obtained in the previous slide. Okay. So again, I have log of A over B here. So I'm going to write this as log A minus log B. So I'm going to get two terms. My first term is this term, and my second term is this term here. I will be doing ARG Max over theta, which means the only terms that matter to me are the terms corresponding to theta, right? I don't really care about the other terms. So this can be safely ignored when I'm doing arg max over theta, right? Now, you'll notice that this term is starting to appear very similar to the expected log likelihood, where really the only difference now is Qij. But I know that Qij, right, the specific form of Qij that will maximize my lower bound are the soft labels Aij. So when I substitute Qij equals to Aij, I actually get the expected complete data log likelihood. So maximizing over this expected complete data log likelihood is equivalent to maximizing over my original objective. Okay. So when I was when I came across these ideas for the first time, I actually came across also a picture that appears in Kevin Murphy's book. So I'll just show that here because this really captures the essence of what is going on, right? So let me try to explain this picture carefully. So here, this red curve is your original function. Okay. So let's say that we are in step T, which means we know what theta T is, right? Theta T, which we obtain from the maximization step, the M step, which means I know what theta T is. This comes from the M step. Okay. So what I do is then obtain a lower bound. So for this theta T, I obtain a lower bound for which I need the soft labels, right? So using this theta t, I get the soft labels, obtain the lower bound. So this lower bound will be the blue curve here. And we notice that this lower bound is going to touch my original function at exactly the point corresponding to theta t, right? And then remember, in order to update your parameters, what I do is I maximize over this blue curve, right? So this blue curve is my lower bound, which is actually being maximized, which means my theta t plus 1 is this point here. This is the update that I get. Now for theta t plus 1, I again obtain soft labels, right? And for those soft labels, I'm going to get another lower bound, which is the green curve here. This is my new lower bound that I obtained for the new labels or soft labels or soft assignments, AIJ, that I obtained using theta t plus 1, okay? And I noticed that this curve, right, will actually touch my original function here. Right? Again, my drawing might not be very neat, but they are really touching at that point. And then what you do is, again, in the next step, what you do is you maximize over this green plot to obtain new theta t plus 1, theta t plus 2. So these are your update parameters that you get in the next step. All right, so this is how the expectation maximization works. So what I tried to do here was to both give you the mechanics of the algorithm itself, how to implement, right? How to obtain different parameters, what the expectation step is doing, what the maximization step is doing. Then I also went into the details of why it is working, right? What exactly is it doing? How did it magically handle that log summation problem, right? So we treated that, so we saw that what we are really doing is taking a lower bound that actually touches your objective function at the points that matter, okay? So with this lecture, right, we are ready to conclude our discussion on the basics of unsupervised learning, which we started in the third module. We will be going over one case study on distributed learning where this idea of expectation maximization will also appear. We won't be, again, since we have done this in a lot of detail here, I won't be going over any details of expectation maximization in that case study. Our goal will be to give more insights about that case study itself. Now, just for completeness in this lecture, we have covered Gaussian mixture models, something that we started in lecture 5. Then we interpreted k-means in terms of a specific Gaussian mixture model where our Gaussians were spherical, right? So that gives us some intuition as to in which cases the k-means is going to work well. Then we also, of course, spent a lot of time on density estimation using the expectation maximization. All right, so thank you so much for your attention, and I will see you in the next lecture.